the title is Giving the Preprocessor a Break with Tracer-Agnostic Instrumentation API, with a tracer-agnostic instrumentation API. All right. Okay, so now time for this talk about libside. So my name is Mathieu Desnoyers, I'm CEO of Efficios, and in my spare time and as work, I do tracing and tooling infrastructure. Outline of this presentation. So I will do a incomplete overview of static instrumentation mechanisms that exist. I will present what recently happened about user events in the Linux kernel. I will then go on to discuss specific APIs that currently exist for user space static instrumentation. Then I will list a list of things we want in terms of user space instrumentation. I will present libside and discuss future work. So what is static instrumentation? So static instrumentation is statically defined within the instrumented code. So it's typically put there by the application developers or the library developers. It allows instrumented application and libraries to express semantic. So whether that can be event names, field types, and much more. Usually it can be enabled dynamically at runtime when needed. So there are a couple of mechanisms to do static instrumentation out there, and this is a non-exhaustive list. But the ones I will target here mostly, so the statically defined tracing SDT, originally from dtrace. It's also implemented by SystemTap on Linux. The Linux kernel trace points that I created back in 2007. Then the LTTNG UST trace points, which I created later on. Then there's the Microsoft trace logging facilities for ETW on Windows, and they did an adaptation to produce LTTNG traces from the trace logging instrumentation as well. So a few words about how libside came to be. So within the Linux 5.18 merge window, I've noticed the appearance of the user events ABI. So it did get in without much community review. And I did, when I noticed that, I did some review and actually asked to have more time to do more thorough review of the ABI that it would expose before it would become stable. So Steve Ross had marked it as broken before 5.18 went out. So it gave us more time to fix the underlying issues. So I did work closely with Bo Belgrave from Microsoft. I provided feedback, which led us to mark it unbroken for 6.4. So some of my main concerns about user events, one of those was that it exposes a stable ABI that allows applications to register their event names and field types to the kernel. So I can expect this to have a large impact on application instrumentation in the future. So my main concerns were that it should be co-designed with a user space instrumentation API and ABI. So I did not want a kernel ABI to specify how user space should be instrumented. Because to me, the kernel tracers are just one user of user space instrumentation, mostly. So my goal there was to allow purely user space tracers. I maintain LTTNG UST, which does all its tracing in user space without even going to the kernel. So I wanted a common instrumentation infrastructure to be usable by both kernel tracer and purely user space tracers. So in my opinion, the tracers can have their very specific use cases, and they each have their little niche, but the infrastructure should be shared. That's true for the Linux kernel with what we did with trace points, k-probes, u-probes, and other. It should be true for the user space ecosystem as well. So my goal there is to limit fragmentation of the instrumentation ecosystem. So I'm going to do a very relevant question would be, why would we need yet another instrumentation API? I mean, there are plenty out there, just pick one. So I'm going to do an overview of what are the limitations of each of the existing instrumentation APIs. So SDT, so its implementation is closely tied to the ELF format. It mainly targets C, C++, so it emits specific sections into the ELF. It has a complex calling convention, so for each architecture, how many of the parameters are received. Its basic support, what it passes as parameter, is basically limited to C basic types and pointers, and the handling of pointer dereference and kind of digging into more structured types, this is left to compiled probe providers that need to be compiled with the application. So it's not natively suitable for other runtimes as far as I know. So for things like Golang, Java, JavaScript, Python, and others. So its main target is C, C++, as I understand it. So it requires breakpoints for instrumentation. So that requires, for Linux and system tap, for instance, I've read well. So system tap can hook onto those SDT points. GDB can also do that. It's not clear to me how it would behave if both would try to instrument the same SDT probe at the same time. Yeah, it would die, I guess. And of course, it requires a round trip to the kernel just to get through the breakpoint. So that already makes it not usable for a purely user space tracer. If the goal is to stay in user space, that's not the solution. So there's no mechanism to coordinate between concurrent use by a kernel and purely user space tracer. So some limitations about the LTT-NG UST trace points, which I created and maintain. So it's really not perfect, and this is why I want to create something new. So the trace points from the LTT-NG UST project, they are based on a compilation of trace point probes. They use, like the Linux kernel trace event, they use a multipass header inclusion trick, which, well, if people get their typing wrong or do mistakes when they create their probe description, the compiler errors are pretty hairy to understand. So it generates a lot of code when the number of trace point signature increases. So let's say you have thousands of different event signatures in your application. Then this is going to generate a lot of code that pollutes your instruction cache when you trace many of those events. So this is not perfect. And also relying on code generation like this prevents the native integration with other runtimes as well. So with Golang, Java, Python, Erlang, JavaScript. So what we have today is kind of logger facilities. So we hook with Java JUL or log4j, but we log strings. Same thing for Python logger. So we log strings. So this is very limited. This is not native integration. We don't have structured data types and complex typing available at all. Also, the dependency on C function prototypes requires us to add additional code when we want to take the trace point arguments and hand them over to things like a dynamic bytecode interpreter or field capture. And this part of the problem, so where we have to take these arguments that we receive, let's say, from a C function signature and kind of lay them on the stack for, let's say, a bytecode interpreter, this is quite similar to the problem we have to solve for the kernel user events. Because if we want to push data to user event, then we want an ABI to actually serialize that information to make it consumable by a user event and therefore by kernel tracers. So the support of nested compound types also is not straightforward for structures, arrays, variable length arrays. So these are types that we have in our common trace format, but that the tracer do not generate through the trace points. And of course, they also just support a single tracer, LTT-NG UST. So some limitations of the trace logging facility from Microsoft, it's mainly overhead. So the way they do it is that they send the metadata along with each event payload. So each event contains its own description about its typing. So this adds a lot of overhead when you do tracing. So if you always do the round trip to a kernel tracer, you may not care that much because it's already relatively slow. But if you do a purely user space tracer, then adding this extra metadata along with each event is increasing the buffer size that you need a lot and taking a lot of overhead hit. So they have no mechanism to pre-register event types and just kind of push the data out on the fastpath. So this is a desiderata of what are the desired features for user space instrumentation that I captured. So one thing that we want is common instrumentation for kernel and purely user space tracers. We want the instrumentation to be self-described. We want to support compound and nested types. And basically, I also gathered feedback at the last Tracing Summit in on-conference sessions with people from Google and others. So this is the result also of brainstorming with other developers as well. A lot of it comes from me, but I did get some feedback. And of course, I'm asking for feedback here. So support for pre-registration of events, for overhead limitation, of course. To not rely on compiled event-specific code, something that is generic, independent from ELF, so, which goes with to natively cover statically typed and dynamically typed languages. To have a stable ABI for instrumented code, kernel and user space tracer. To support concurrent tracers and to expose an API that allows dynamic instrumentation libraries to register their events and payload. So with this, so this is really setting up the overview of what led me to create libside, what was incomplete in the existing static instrumentation solution, and this is what I came up with to answer all those constraints. So libside, it's a backronym, so it stands for Software Instrumentation Dynamically Enabled. Doesn't mean much, but that's the name of the project I came up with. So it really has two APIs and ABIs. It's actually not just APIs, but it's also meant to be ABI. So there's a part of it that's for the instrumentation, so it has a type system, helper macros for C and C++. It allows it expresses instrumentation description as data, and the instrumentation arguments are passed on the stack as an array. So this is really similar to what the kernel does with IOVec. So read v, write v. So you get an argument vector of what is the data that needs to be read, what are the chunks of data. But here, instead of having each of the IOVec element being a pointer and a length, we get a type, and either its content or a pointer to its content. So that's basically the key of it is really that concept. So this is the main ABI for kind of sending data over. And this actually, I got from a discussion with the Microsoft guys, because they use that kind of technique in their trace logger. So there are good things in the trace logger facilities, but kind of combining this approach with pre-registration of events, I think, is the key there. Then the instrumentation is conditionally enabled when at least one tracer is registered to it. And then for the API and ABI for the tracer, so it's tracer-agnostic. So the tracer can register to get notified about available events. So it knows which events are present in the application. It can conditionally enable instrumentation. The synchronization of registered user space tracer callbacks is done with a RCU implementation within libside, so it's purely user space RCU. And it's, as I created libside, I co-designed it with Bo Belgrave so that user events could interact with libside. So the integration is not completely done, but we have proof of concept that shows that at least it connects, it fits together. So that's an example of the field description ABI that we have in libside. So you'll see we have those data structures that can be directly used by runtimes that want to interact with libside, and then we have helper macros that help kind of just declaring this and using this from C and C++ code. So that's an example of a 32-bit signed integer. So here we have the side type, we have one of its type is the side integer, and then we have all the fields, so the integer size, its length in bits, its signedness, its byte order. So this is its description. There are also attributes that I will talk about in a few moments. Those are optional. Then we have the event. So the first one was the field description. This one is the event description. So the event has what? It has a couple of attributes. So it's enabled state, it has a name, it has fields and callbacks, flags, version, and whatnot, log level. And then the fields, it's an array of tuples, field name, and a type. The event arguments ABI, as an example, so this is how this integer argument is passed on the stack when the instrumentation is called. So at the bottom, we can see a side arc vector. So this is a vector of side argument. Think of it as an IO vector for now. And then each side argument, it has a type, and then it has a union. Here we have a static type. This static type is an integer, and then we have its content. So that's how it's passed on the stack. There are helper macros to help using this from C and C++. This is a small program which has which includes the side trace.h header. It declares an event with a identifier, a name, log level. It has a field list with its type, and then in main we just do a side event. It will conditionally call the instrumentation if used by a tracer. It refers to it by the identifier and then the argument list. So I created a demo tracer in the libside project. It just pretty prints on the console whatever the tracer would record. So in this case, we can see the notification about the events being loaded actually. And then we can see the event firing off. So we have the event with the name, with the fields and everything. So there are a couple of types that are supported, and part of the feedback I want is which ones are actually needed. So some of them come from actual user requirements that I got from end users. But at some point it's good to kind of go back and see, okay, are there some that we should remove before cutting a release of that ABI? So we have the basic types that are copied on the stack. We can see there, so a null, Boolean type, the signed and unsigned integer, the byte, the pointer, floating point, fixed size, and then the UTF-8, 16, and 32 strings. We have also compound types, structure, variant, arrays, variable length arrays. We have the enumeration type, the enumeration. We also have the enum bitmap. So this is really a bitmap where each bit has a name. So if the bit is enabled, that name gets shown let's say, by the tracer. So this is a fairly common pattern in the way the Linux kernel trace points are used. And then we have also a placeholder for dynamic types. So I took that name gather type, it's from scatter gather, but there's no scatter to do. It's just gathering things in the application memory. So rather than copying data on the stack, we basically have references to the application memory that should be used as source for the data when we hit the instrumentation. So we have all those types. The dynamic types, So there are some use cases where we cannot know in advance, or it would be really cumbersome to kind of list in advance every possible type that can be received by the instrumentation. So this part about dynamic type is, well, it's really like trace logger from Microsoft, where you can specify along with your event payload what is the type. So this is really more flexible, but it adds overhead, and it's meant to have in your data the meta information that describes the data. So in terms of event and type attributes, so there are key value pairs that can be optionally specified. It can allow tracer-specific custom extension and pretty printing hints. This is an example of pretty printing hint of unsigned 16 field, where we have an integer base attribute that specifies that it's in base 2. So when it pretty prints, whatever reads the trace will be printing as a binary like this. Then another example, more complex, a formatted string example. So we also have the side static event variadic, which takes some fields that are known statically and other fields which are dynamically typed. So with this, what we can do is basically implement a format string. So the format string is the statically known string field, and we can see it here. So the side field string FMT, and then we can apply to it an attribute which would say, well, this is a language C format string. So whatever trace reader knows about it can actually do the pretty printing if they choose to. And then when we do the side event call variadic, then we have the format string, and then we have the list of variadic fields, where then we can see the result. So, so we did define the vector of arguments just before the call. We had a string, we had a signed integer, and then we have the result. So here we are not doing the pretty printing, but we have all the relevant information in the trace to do that pretty printing if we choose to do so. So how tracers interact with libside. So a user space tracer will register callbacks to be notified when a new event description is available or when it goes away. It registers callback to be called when an event is emitted. And a kernel tracer. So libside would invoke the user event IOCTLs. So that user event then can modify the enabled state by setting a reserved bit when it wishes to be enabled for a specific event. So in terms of future work, so I did not do the extensibility part of the libside ABI. So currently those are all kind of a fixed pack structure without any way to extend or version or anything. So we'd have to think carefully about, well, if we want to add something, how would we do it? And do we ever want to do it, or how do we want to handle extensibility? So this is always a tricky part about things like system calls. And I kind of see libside not only as an API, but as an ABI between various runtimes and the libside library, but also between libside and user events eventually. So it will be important to get this right before cutting a release. Another point is the portability of the libside ABI. So currently I use pointers in my structures, which is really bad if you want to have a 64-bit kernel touch structures from 32-bit applications. So what I plan to do is to basically create a small wrappers that will use a UN64T type for all pointers, but then I will put that in a union that will have also the type of the pointer. So basically I can, with wrappers, with my wrapper macros, I can cast between this unsigned 64T and the pointer type. So I want to keep the pointer type in user space to get the verification from the compiler, but I want to use that to be backed by a UN64 for portability reasons and compatibility with kernels with different bit size. So another step will be to reevaluate the usefulness of each supported types. Maybe there are some that are redundant in terms of covering use cases. So all the types we have there require the tracers to support each of these. So it's added complexity. So it's always good to think twice about this before doing a release. Then there's a step, a fairly large step of integrating with LTTNG UST. So the road ahead there, registering LTTNG UST as a libside tracer, implementing event registration notification callbacks, translate libside event descriptions to bytecode. So the thing is, I don't want my tracer fastpath to kind of marshal over those rather, well, those data structures. What I want to do is, upon registration, once I want to marshal those data structures, generate a bytecode, and then have an efficient bytecode interpreter do the ring buffer serialization, apply the filter runtime, the runtime filter, or do field capture. Then another future step would be to integrate libpatch, which does dynamic instrumentation, with LTTNG UST through libside. So libpatch could use libside to kind of declare the field types that it wants to record and things like that. And then there's another step of future work, which is integration with user event. So that's what I have. Now we have a bit of time for questions. Opening the microphone. It's okay.
You've answered nearly all my questions already, in particular user events, and is making me bubble over about a better implementation for dtrace USDT, which could suddenly gain support for all libside users. But the worry I had was regarding your pointer sizing thing. Using a uint64T rather than the uint-putter-T means that this ABI would not be compatible with Cherry and ARM Morello.
Sharing with what? Sorry?
With Cherry and ARM Morello, which is a very nice scheme using 128-bit wide pointers to encode things like bounds and so on and so forth for hardware-assisted bounds checking and that sort of thing. And almost the entirety of Unix systems, including things like X, can be ported without trouble. But they all have to switch to using uint-putter-T, and they need to be basically agnostic to pointer sizes. So you might want to say that 32, 64, and 128-bit pointers are three separate variants in some way, and have an ABI adjust or have three variants of the ABI or something. And then you'd be magically compatible with Morello without needing to do anything.
Yeah, so the part about pointers versus uint64, this is just about the description of events. This is not about what we do on the fastpath in terms of capturing pointers. So I have a pointer type specifically for capturing pointers from the application, and I plan that to stay there.
Right.
But I'm not sure your comment applies to which of those parts.
Yeah, on a Morello system, all pointers are 128-bit with capability bits attached, embedded in the 128-bit pointer. Any attempt to strip the capability bits off and go down to 64 bits produces a pointer that would fault immediately if you try to use it. So it's worth at least noting that systems like that exist.
So you're worried about systems with 128-bit pointers that have those specific capability bits?
They're real now.
I have not considered that yet. I'd have to have a look to see what are the impacts.
They're fabulous. Have a look.
Yeah, thanks.
Other question?
Yeah.
I had a question about the callbacks. It's kind of compound. One, are the callbacks executed basically in line with wherever like events are being emitted, so like that the function call to the callback is put there, or is there something in between? And then related is, are there like requirements on what the user space callbacks in terms of performance or other kinds of restrictions to like successfully implement a callback?
The callbacks are executed in line. They are, I mean, you won't want to, let's say, take a mutex in your callback that could create a deadlock with your application because you are called inline, right? So you want to try to minimize both the overhead and the overall impact that you have within that callback, because you can be called from any trace point you connect to. Yeah. Thank you.
Thank you, EJ.
One more question?
Have you considered integrating with other tracing frameworks like OpenTelemetry, like capturing a correlation ID that's more than just about a single machine that you could post-process, or other tracing frameworks like I recently read about Tracy, which is most like something used for games, but it is very low latency, so it would look like libside would be useful to be integrated with Tracy.
Yeah, that's another topic on its own. I think there is a presentation about integration of OpenTelemetry with LTTNG later today. But the short story is, I'm not sure it belongs in libside per se. Maybe, I don't know. But I think kind of having a way to capture a current span ID information and keep that in a thread local storage available for tracers might be really useful. So I'm really open to this. I just don't know at which layer it should sit. I mean, should it be in libside? Not sure, because libside is really about receiving information from specific execution context. That could sit in a different library as a storage available for current span ID or something like that. But I mean, I'm open to discussion. Those are excellent points to add to the whiteboards so we can have further discussion in the unconference session. Thank you.
Thank you, Edwin. Other question? All right. Before we go to the break, I just want to mention that we have a board there. If you can write down any subject you want to talk on the unconference. So the unconference is not only one subject, it could be multiple subjects. We form groups to talk about the subject. So if you have a subject, write it down on the board there. And if you, perhaps not too bored because we don't want to waste 2 sheets of paper for that. Just write down a subject, and if you don't have a subject in mind but you're interested in subjects, you can put a plus beside multiple subjects. And then at the end of the day, we will decide, we will form groups around subjects that are the most popular. Okay? And we will be back at 11:30, so we have a 16 minutes break right now. Thank you.
If I can just say, so if you're looking for the organizers of the Tracing Summit, which I forgot to mention, so there's myself, Mathieu Desnoyers, we have Olivier Dion, also co-organizer, and Erika Bogdan. So feel free to ask us if you have any questions. So back in 15 minutes. Thank you.